This is Unit 4 Practice Exam B for Math 1060. Okay, putting a point in polar coordinates, the radius here and the angle. Radius is positive, so we're on this third circle out at an angle of 5 pi over 6 right here. When we're converting from polar coordinates into rectangular coordinates, we need rectangular coordinates have an x and a y coordinate, so we need to have the x coordinate and we need to have the y. The r value is 2, and then cosine of 5 pi over 6. The y value is 2 times the sine of 5 pi over 6. Well, the cosine of 5 pi over 6 is negative 3 root 2. 2 times negative root 3 over 2. And then at 5 pi over 6, sine of 5 pi over 6 is 1 half. So this is 2 times 1 half. The point in rectangular coordinates turns into negative square root of 3 comma 1. Now going the other direction, if this is in rectangular coordinates already, we need to convert to polar coordinates. Specifically, the r values bigger than 0 and the angles between 0 and 2 pi. So in polar coordinates, we need the r value. So that's Pythagorean theorem. We'll start with that. So this is 4 times 3, which is 12. So the r value is 4. Now the angle is inverse tangent of y divided by x. So it's the inverse tangent of the square of 3. And that's equal to pi over 3. Now this coordinate here is in quadrant 4. So we now need to use this angle pi thirds as a reference angle to get an angle in quadrant 4. So in quadrant 4, we hit 5 pi thirds. So the r value is 4, and the angle is 5 pi over 3. Multiplying two complex numbers together, um, rather than keeping them in rectangular form like that, we're going to convert them to a polar form. So first we'll take negative 2 minus 3i. So we need r. So this is 4 plus 9, so that's square root of 13. And then theta is the inverse tangent of 3 halves. So that's not going to be a value from the unit circle. we'll just estimate here. It's 0.9828 radians. Now this is in quadrant 1. However, this complex number would be in quadrant 3. So we need to add pi to this. So pi plus 0.9828 is 4.124. Okay, so now for the other one, the square root of 40, and then theta, inverse tangent of 2 over 6, which is 0.322 radians. But this is in quadrant 4. So if we subtract 0.322 from 2 pi, then we're going to get 5.961. Okay. So what we have then is this product becomes the product of two complex numbers in polar form. We have square root of 13 cosine plus I sine of 4.124 times square root of 40 times the cosine plus I sine of 5.961. So when you multiply two complex numbers in polar form, you multiply the two moduli together. So the square root of 13 times the square root of 40, if you multiply 13 times 40, that's the square root of 520. And then you add the two arguments together. So 4.124 add to 5.961 gives 10.086. And then we can convert that back into rectangular form. So we need the square root of 520 times the cosine of 10.086. And that's equal to negative 18. And then we need square root of 520 times the sine of 10.086. And that's equal to negative 14. Now, luckily, part B is already in polar form. When you're dividing two complex numbers in polar form, you divide the modulus of the numerator divided by the modulus of the denominator. And you subtract the two arguments. So we have 240 minus 270. We need to change that into rectangular form now. So this is 5/4 times the cosine of negative 30 degrees. So at negative 30 degrees, the cosine is square root 3 over 2. So this is 5/4 times square root 3 over 2. And then the sine would be negative 1/2. So this would be 5 square root of 3 over 8 minus 5 over 8 pi. Part C, raising a complex number to a power, to Moss theorem. We are going to first, again, change that complex number from rectangular form into polar form. So we need R. This is the square root of 8, which is 2 root 2, and then we need theta is the inverse tangent of 2 divided by 2. This is the inverse tangent of 1, which happens at pi 4s. Now, this complex number is in quadrant 4. So in quadrant 4, we're going to get 7 pi 4s. So we have a complex number in polar form of 2 square roots of 2 times the cosine plus I sine of 7 pi 4s. And we're going to raise this to the 4th power. So for de Moss theorem, we have the modulus that's raised to that power. Times the cosine plus I sine, and then the argument is multiplied by that. So it's 4 times 7 pi over 4. So 2 root 2 to the 4th power, 2 to the 4th power 16. And the square root of 2 to the 4th power is 4. So 16 times 4 is 64. Cosine plus I sine of 7 pi. So now changing this back into rectangular form, we have 64 and then cosine of 7 pi is -1 and the sine of 7 pi is 0. So this is equal to -64. For question 4, we need to find the 4th roots of z equals 81. So in rectangular form, it's 81 plus 0i. So in polar form, r is 81. And the argument is 0 radians. So really what we're trying to find now is 81 times cosine plus I sine of 0 radians. The 4th root is the same thing as an exponent of 1/4. So according to de Moss theorem, this is going to be the modulus raised to that power times the cosine plus I sine. The argument is divided by however many roots, so in this case 4 plus 2 pi divided by 4 times k. And we need 4 cases of this, so we get the 4th roots. So it's going to be 0, 1, 2, and 3. So the first root is when k is equal to 0. If k is equal to 0, this turns into 0. And 81 to the 1/4 is 3. So at 0 radians, the cosine is 1, and the sine is 0. So this is equal to 3. In the case when k equals 1, then we have 2 pi over 4, which is pi halves. This is 3 times the cosine plus I sine of pi halves. So at pi halves, cosine is 0 and sine is equal to 1. So it'd be 0 plus 1i, which is 3i. In the case where k is equal to 2, then we have 4 pi over 4, which is pi. Into pi radians, cosine is equal to -1 and sine is equal to 0. So that's equal to -3. In the case when k is equal to 3, we have 3 times 2, which is 6. 6 divided by 4 is 3 over 2. So this is 3 pi halves. Cosine of 3 pi halves is 0. And the sine of 3 pi halves is -1. So there we have all fourth roots of 81. Okay, for question 5, we've been given the initial point and terminal point of a vector. So just need to write this as a linear combination of terms in I and j. So basically the component form where the initial point is on the origin. So we're just going to subtract 6 minus -3. That's 9. And then 3 minus 3 is 0. So you can write it as 0j, but really it would just simplify to 9i. Now the really understanding this is the horizontal component, this is the vertical component. So this vector only has a horizontal component of 9i. That means it's running 9 units along the horizontal axis. So the magnitude is 9, and the direction, since it's running right along that positive x-axis, the direction is 0 degrees. Now question 6, when we have the magnitude and the direction, we need to find the component form. So we need the x value and we need the y value of the horizontal component and the vertical component. So the horizontal component, I'm going to say x, is equal to the magnitude times the cosine of the direction angle. So this vector v lies in quadrant 4, and it makes a 60-degree angle with the positive x-axis. So we can either write that angle as -60 then, or as 300 degrees. I'm going to write it as 300 degrees. So then the vertical component is going to be 7 times the sine of 300 degrees. And then 300 degrees is one of our unit circle angles. So 300 degrees, we have cosine is 1/2. And the sine of 300 degrees is -√3 over 2. So the component form of this vector is 7/2, comma, -7 square roots of 3 divided by 2. Question 7. 2v is equal to the components of v multiplied by 2, so it's negative 6. I'm at 8. For w is all the components of w multiplied by 4. So if we have negative 6, subtract negative 8, that's 2. And then if we have 8, subtract negative 28, 36. Now the angle between the two vectors, that was one of the properties or the applications of the dot product. So the cosine of the angle between the two vectors is the ratio of, in the numerator, the dot product, and in the denominator is the product of the two magnitudes. So first, let's find the dot product of v and w. So the dot product is that linear combination, the product of the horizontal components added to the product of the vertical components. So the horizontal components, negative 3 times negative 2 is 6. The vertical components, 4 times negative 7 is negative 28. So we get negative 22. Magnitude of v this is 9 plus 16. That's 5. And then the magnitude of w that's 4 plus 49. So then cosine theta is equal to negative 22 divided by 5 times the square root of 53. It's negative 0.604. So inverse cosine is 127.18 degrees. Okay, question 8. This airplane leaves the airport 225 miles per hour bearing 50 degrees west of north. And there's a 20 mile per hour blowing at a bearing east 20 degrees of north. 20 mile per hour wind, 20 degrees east. Find the true speed of the plane rounded to the nearest mile per hour and the true bearing. So really what we're doing is just finding the resultant vector here. If we were to do this geometrically, if I took this vector representing the wind and place it up here, and the resultant vector would look like that. So we need to find that resultant vector there by adding these two. So we need to find the vector that represents the airplane. So we know it has a magnitude of 225, and the bearing is 50 degrees west of north, so that's 140 degrees as a direction, as a vector. So for the vector, let's call that the airplane vector. the horizontal component is going to be the magnitude times the cosine, and then the vertical component is going to be the magnitude times the sine. So we get negative 172.36 comma 144.63. We get the wind vector. The horizontal component is going to be the magnitude times the cosine of the direction. Now the bearing is 20 degrees east, so that means that there's 70 degrees in that x-axis. So cosine of 70, and then the vertical component is going to be magnitude times the sine. This is going to be 6.84 and 18.79. For the resultant vector, if we add the two horizontal components and then add the two vertical components, we're going to get negative 165.52 for the horizontal component. And for the vertical component, if we add the two vertical of the airplane and the wind, we're going to get 163.42. That's the vector representing the true speed and the true bearing of the plane. So now we just need to find the magnitude of that for the speed. And that's roughly 232, and it says to the nearest mile per hour, so 233 miles per hour. And then the direction getting about 45 degrees from this. So in quadrant 2, that's 135 degrees. So then the bearing would be 45 degrees west of north. So let's see, I'm going to put this. The true speed is 233. The true bearing is 45 degrees west of north. Okay, the work done. This was one of the applications of the dot product. The work done is the dot product of the force vector and the displacement vector. So we have a wagon here. And the handle makes a 20-degree angle. And the displacement vector is 50 degrees horizontally. but the force is 25 pounds. But for the force vector, we need to find the horizontal and vertical components. So the horizontal component is going to be the magnitude times the cosine. And then the vertical is going to be the magnitude times the sine of the angle. This is about 23.49. And this is 8.55. So then the dot product is going to be that linear combination, the product of the two horizontal components. So that's 1,174.62 plus the product of the two vertical components is 0. So this is 1,174.62 pounds.